I'm going to teach you about something called mechanism. Actually, as I'm reading through this, 4B and 4C are just ridiculously closely entwined. So we're going to treat them as one sort of unit. In 4A, we learned about rate laws. And more specifically, how to experimentally determine the rate law.
Yes, sir.
Right? And what a rate was. Okay? What is the point of knowing the rate law? Well, one, we can know how long a reaction might take if we want to produce a certain amount of stuff. We might also be able to control how fast the reaction goes. If we want to try to prevent heat from building up or something like that, if we're working in a factory or something like that. Okay? Another reason to investigate the rate laws is that it can actually tell us something about how the reaction actually occurs. Okay, so a mechanism is actually a process by which a chemical reaction occurs. What do I mean by that? Well, let's say we have a reaction like H2 plus O2 yields H2O. Not balanced,
Yeah.
so. All right. This is the overall reaction. But it doesn't tell us how that reaction actually occurs. So what we try to do is we try to come up with what are called mechanisms. And the mechanism is how this thing actually works. The steps, yes. So the step-by-step process. We know that for a chemical reaction to occur, particles have to collide and rearrange their bonds. Okay, so what we want to know is what are the step-by-step collisions that take place in order for this reaction to occur. Now, there are many, many possible ways this reaction could occur. So we are free to propose any mechanism that we want. The thing about the mechanism is it must consist of a series of what we call elementary steps. An elementary step is a reaction that actually describes a collision. Okay? So, mechanism one. It is possible that this reaction occurs in one step. In one collision of two H2 molecules and one O2 molecule to produce two H2O molecules. However, let's think about that from an actual physical standpoint. If we have an O2 molecule and we have two H2 molecules, then in order to make, in one collision, two H2Os, these things would probably have to be coming in here exactly sort of, perpendicular to that oxygen-oxygen double bond. They'd have to hit it exactly the right time, right? And they'd have to form their OH bonds all at the same time, and then also break apart that OO double bond all in one miraculous collision.
That's what random chance is for.
That's what random chance is for. Yes. Is it possible that this happens? Yes. Is it the most likely mechanism? Probably not.
The only one we got so far.
Okay. It's the only one I've proposed so far. Now, what are the ways that, just because we can propose a mechanism, how do we know whether our mechanism is correct or not? Well, if a mechanism is a product of a series of elementary reactions or steps, if we're actually talking about elementary reactions, then we can write a rate law just based on an elementary reaction. So if this is my entire mechanism, a one-step process where we have just one collision of three particles, then I can actually write a rate law just based on the coefficients in this equation. So for this mechanism, I can rate that the rate law is K times the concentration of H2 squared times the concentration of O2 to the first. Why? Because if this is actually the collision that occurs, then if we put more O2 in the system, there's going to be more of these collisions, right? The more of these collisions there are, the more likely we're going to get a successful collision and the rate's going to increase. Okay? But because this collision also involves two H2s coming in here, as I increase the concentration of H2, I'm not just going to say if I double H2, I'm not just going to double the number of these collisions. I'm actually going to quadruple it because I'm doubling the chance of we're getting a correct collision over here, and I'm doubling the chance that we get a correct collision over here. So the actual chance of successful collisions is 4 times greater. Okay, so only because I'm assuming this occurs in one step can I write this rate law based on the coefficients of the equation. Now, what if we go into the lab and we do the experiment and we find it's not second order in H2? Then this mechanism is bullcrap. Okay? So that's sort of the process. We do that experimental process of determining the rate law partially to help us try to figure out how a reaction actually occurs. What is the step-by-step, collision-by-collision process by which this reaction occurs? Another possibility. Another mechanism. Well, let's see. What else could happen? So instead of having 3 particles all collide in the same region of space at exactly the same time with exactly the correct orientation and energy, which is very, very, very unlikely, can we think of some collisions that would involve just 2 molecules colliding that might give us the same overall result? Well, I suppose it's possible that an H2 could collide with an O2. And as these collide, maybe we get the H's combining with the O's, so maybe we get 2 HOs out of this. Seems reasonable, right? Definitely more reasonable than trying to get 3 particles colliding at exactly the same time. Yes, we have some orientation issues here, right? They have to be oriented correctly, right? But a 2-particle collision is much more likely than a 3-particle collision. Okay? But this is just the first step, because this has not produced what we're trying to produce. We haven't made H2O, so it's not just a 1-step or a 1-collision reaction. So, well, we've got these HOs, so what are we going to do? Maybe the HO combines with another H2, and forms, maybe if we do it like this and they collide, maybe this OH grabs onto one of these H's and the other one comes flying off, so we get something like that. This would be step 2. Okay? But we're not done because we've only made 1 H2O. We got to make 2 H2Os, right? In addition, we've made 2 HOs in step 1, but we only used one of them up. Okay, so maybe a third step is that that other HO combines with this single H and creates our second H2O. So this is another alternate mechanism, a possible step-by-step, collision-by-collision way that this reaction might occur. Now, each of these steps actually involving the collisions of particles, we can write a rate law for each of these steps. Since this one contains one H2 and one O2, we can write the rate law like that. This step, we could write the rate law as being some k value times HO times H2 to the first. Both of these to the first, right? Because there's one of each molecule needed in the collision. And then this last step, the rate law can be written as k times HO to the first times H to the first. Okay? Now again, how do we know whether this mechanism is true or not? Well, really, we've got about three things that we really want to look for to tell us whether a mechanism is a good mechanism or not. First of all, I have to make sure that when I add up all these steps, I get the same overall reaction I was looking for. So this is kind of like when we did net ionic equations. And we found, oh, there's something the same on both sides of the reaction, we can cancel it out. Something similar is going to happen here. If I add together everything that we have on the left side, I've got two H2s, I've got an O2, I've got two H's, and an H. On the product side, still got my two H's, I got two H2O's, and I have an H. So do we have anything that was present on the left and the right sides?
Drop the hose.
Drop the hose. And the H. Right? So what's left is the overall reaction we were looking for. That's good. That's the first test. If we don't get the reaction we were looking for, the mechanism's terrible to begin with. Okay, the second test is that one of these steps, one of these three steps, is going to be what we call the rate determining step. And to show you the concept of a rate determining step, I've got a little setup here with three funnels. Who's got a stopwatch?
I got you.
Oh, I have a phone. Yeah.
Make it so. Okay, we're going to see how long it takes me to pour this beaker of water through these three funnels. Are you ready?
It's faster if you don't use the phone.
Ready, set, go.
It's getting everywhere.
Stop. 17 seconds on the dot. Cool. Okay, well now I'm going to rearrange the order in which I do this.
Oh, no.
Oh my god.
Is it going to happen faster or slower?
Same, yeah.
Oh, same.
Bottleneck.
Yeah, so you have to wait for the winner.
Let's try it. Ready? Go. Way faster when you spill it all over. Oh, this top one sucks.
Yeah.
Stop! 17 seconds again!
You like spilled all.
Yes, if I hadn't spilled all kind, I should have lowered this funnel too.
Or
Okay.
just maybe
But
like not jammed in.
The point is, it shouldn't really matter in what order we do this, right? Because there's one funnel that limits how quickly I can get stuff through this system, right? This is the rate determining funnel right here, okay? In a mechanism, one of these three steps is going to be what we call the rate determining step. One of these steps is going to be slower than the others. And so even though I've written three rate laws, only one of them actually matters. Because one of them is going to be slower than the others. And if the others are faster, I don't really care how fast that I can get those to occur, right? I could use the world's most gigantic funnel with a 6-foot wide hole. It doesn't matter if I've got this little guy in the system. right? I can only pour it through as fast as this slowest funnel allows. Okay? So, if we actually go in and we find that the first step is the slow step.
Get rid of it.
Let's say this one is slow, and these two are fast. Well, again, these rate laws no longer matter. Doesn't matter how fast step 2 and step 3 occurs, because we're going to be waiting for step 1 to occur. As soon as step 1 is done, the other two are going to blast right through, right? Well, if step 1 is the slow step, then this is the rate law for this mechanism, right? And so if we did the experiment and we found it was first order with H2 and first order with O2, then this mechanism gets even more likely to be true. Right? Because the overall experimental rate law matched the slowest step of our mechanism, and the slowest step of our mechanism always controls how fast the reaction can occur. Adrian, question? Just let it soak in.
It makes so sense.
That furrowed brow, like, oh, I don't know what's going on. You cool?
How do you know which one's the slower?
How do you know which one's the slow step? Great question. Well, you can think about things like how likely each of these collisions is, right? So when I talked about the H2 combining with the O2, that sort of had to have a certain orientation, right? And so somewhere in this K value is that idea that the particles have to be oriented correctly, right? So this one might have a smaller K value than these. Okay, this one where we just have this H colliding with the OH, probably possible that there's several orientations that H can come in
So
at.
it's faster.
So it might be faster that way. So there might be orientation effects that make it faster. There also might be energy effects, right? Because here we actually have to break some bonds. We have to break the HH bond and the OH bond, right? So then the energy part of the K might come into play, right? This might require a larger amount of activation energy, and so it might be slower. Okay, now also in this section, I think it's actually in 4B3, it says a successful collision can be viewed as following a reaction path with an associated energy profile. So for this three-step mechanism that I have proposed, there's going to be some profile, energy profile. So this is like one of those exothermic, endothermic curves that you guys have seen before. Except if we have three steps, it's not going to be as simple as the types of graphs that you've seen before. We're starting off with a step that is extremely slow. If that step is slow, it probably has some high activation energy. Right? So it's possible that for this reaction, you might have a reaction coordinate or a reaction path that looks something like this. And the bumps are each describing one of these steps. So this would be step 1, step 2, and step 3. Okay? Now it's also possible that this same reaction has the profile like this. But if the profile looked like this, and this was step 1, and this was step 2, and this was step 3, then step 1 wouldn't be the slow step, right? Whichever step has the highest activation energy, that's going to be our slowest step, for reasons we talked about yesterday, right? The high activation energy, when we think about the Maxwell-Boltzmann distribution, if all the particles have their distribution of energies, and this is the activation energy for step 1, and this is the activation energy for step 2, then a much smaller fraction of particles are going to undergo step 1 in a given amount of time than are going to undergo step 2. That makes sense? All right. Now I also want to talk about these hose. These HO molecules that we've produced here. What are they? Reactants or products?
Yes.
Yeah.
Scantily dressed.
Well, they're kind of like.
The correct answer is neither. Because on this graph, reactants are here, right? And our reactants are H2 and O2. Our products are down here. And our products are H2Os. So what are we going to call these hose?
Not.
Well, they are substances that occur in between the time when we have reactants and the time when we have products. We call them intermediates. So HO is what we call an intermediate. It's produced in one step of this mechanism, but then it's used up in a subsequent step. That's a key feature of intermediates. They're only present for a short period of time. They get produced, but then they get used up. So we're not going to see any hose at the end of this reaction. They're all turned into something else.
Wonderful people.
Millionaires.
Millionaire beauty queens.
Or facilities.
Now, intermediates are extremely important in proving your mechanism. So I said the first two things you have to absolutely make sure are true of your mechanism is one, that it adds up to the same overall equation. Two, that the rate law for its slow step matches the experimental rate law. If that's not true, then your mechanism's bullcrap anyway, right? But the third piece of evidence you might use to try to convince people that your mechanism is the correct mechanism is the presence of some intermediates. So if this thing, HO, has a color, for example, and we see that color being produced during the chemical reaction, that leads even more evidence towards this being the correct mechanism. Okay? And there are definitely some experiments where we can see something being produced that's not there at the beginning and it's not there at the end. So I want to show you that real quick.
Yay.
Oh, is that what that was?
Are we doing it?
That.
All right. I'm going to take a little bottle with some hydrogen peroxide in here. This is 30% hydrogen peroxide, not your mama's peroxide.
Mom uses.
Your mama's is 3%.
Nah, she uses the strong side.
She puts 30% on you. You're dirty.
No, more than that.
No, this stuff will actually cause chemical burns. I've spilled this on my hands and it like bleaches your whole hand and it hurts, it burns, it's pretty nasty. Okay, so what I'm going to do to this is going to add something called potassium iodide. It's actually dissolved in water, so this is a potassium iodide solution. The potassium iodide is actually a catalyst for this reaction. We're going to talk about catalysts later next week. All right, but they speed up chemical reactions. But what I want you to do is to notice that we have a clear colorless liquid here and a very slightly yellow, but basically clear and colorless liquid here. When I pour them together,
Oh god.
Elephant cheese. Oh no. We tried.
I'm gonna just.
Elephant cheese.
Oh yeah,
Hey.
it's my favorite drink.
It's
Oh
slurm.
Slushies.
Slurm. That's how they make
Add
slurm.
more.
Yeah, pretty much. Do it
I
again.
didn't see it.
And that's how they make them.
You do it again.
now, actually what I was expecting to happen,
Is a volcano there?
you alright?
Yeah, fine.
You scared of my reactions? Okay. Well, it's close. Let's stir it up just a little bit more here.
Gonna turn plus.
Because, did you guys see what happened at the very beginning?
Oh, there.
Change the color.
it turned like really, really dark brown,
Yeah.
right? And now here, it's
Orange.
still a little bit orangish color.
It's
Okay.
Coca-Cola.
Caramel.
Take a drink.
Kind of caramel color, but definitely not that dark brown that we had before. Okay? Now, that dark brown, it's possible that that was an intermediate that was being formed as the reaction occurred, but then it got used up, so we don't see that dark brown color. It's possible that this slightly orangish color, maybe there's a little bit of intermediate that's still left in there that just hasn't found any other reactants to react with and completely get used up, okay? But I was actually kind of hoping that it would go back to colorless.
Do it again.
Do it
Do it again.
More.
Hey, it's colorless now.
You did it. You did it.
No, it's good.
I'm gonna put less in there. I don't want it to come spraying out of it.
More.
Wait.
More. One for the homie.
One for the homes.
Now there's actually still potassium iodide in there, so when I pour this in, it's possible that it's going to react.
Oh, no worries. You wait until I got back over here. I like the fumes.
Well, the fumes are basically just water vapor, so
Yeah, what did you think it was?
water vapor.
Yeah.
He knows that.
Oh. Oh. Oh.
Excited. Okay,
Oh,
so
it's-
this time
It's more.
Keep going.
still a little bit yellow, but
Again.
But it's light.
definitely lighter. Okay. Again, keep going. Where did I put that green tray?
We ate it.
What?
Myra, I'm hungry.
Is that back
Can't
there?
give me a
Oh,
Oh, it's over there.
okay. Just because it's such a cool experiment, I want to do this one more time
Yes.
It's like Tommy Bartlett.
in a slightly different way.
No goggles.
Are you gonna do the phone thing?
Are you gonna do the volcano? Wait, are you gonna record it?
Shh. Okay, I'm gonna do it in this cylinder so it doesn't build up pressure and spray all over. Awesome.
Can I record it?
Sure. So what I'm gonna do this time is add a little bit of dish soap.
Gotta clean
You
this
tell
up
us when the reaction.
and all the things.
Sure, I'll give you the Snapchat countdown.
Yeah.
All right, so I'm going to add the catalyst in 3,
It's the way we clean.
2, 1. Okay, so that time if you were watching or if you go back and rewatch your Snapchat, you'll see it turns really, really dark brown at first.
What's your problem with brown, man?
Can I touch it?
Can you touch it? Yes,
Can I touch it?
theoretically. Theoretically, because the hydrogen peroxide is dangerous, but
It's not.
the product should just be H2O. And this yellow stuff, this potassium iodide, is actually the same, similar to the stuff that they put on you to disinfect if you like get blood drawn. You ever have where they put that really dark yellow iodine
Now
stuff?
it's blue, right? No, it's pink.
It still looks yellow to me, man. I don't.
No,
It's
I-
yellow,
it's
but
something
it's
used-
very, very light yellow. Whereas when it first happened, it was like super dark brown. Okay, so the point I was trying to make there is that it's possible that whatever that brown was an intermediate. It got produced for a brief period of time, but then it got used up in another step, so it's not there at the end of the reaction. Okay? So intermediates is a really good way of trying to lend some evidence that your mechanism is a correct mechanism. All right?
Oh, look at it in slow motion.
Slow motion. All right. Other things. If we have this reaction profile, where would the intermediates appear?
Probably in the.
At the top.
Yeah, they're in these little valleys here. And each of these valleys is where we have created
Can I-
our intermediates.
Come on.
Where my pen go? Up your bottom.
we talked about the valleys. What about the peaks?
What about it?
What would the peaks represent?
Bond.
Well, we talked about the difference in height being related to
Oh,
what?
is that when the reaction started?
Activation.
The activation energy, right? So how high that peak is tells us the activation energy. But what does that mean? Activation energy. I think yesterday somebody gave me the fantastic definition, the energy of activation.
Wait,
What?
Are you guys
Is
just
the energy
saying
you need to break those
you
bonds?
require enough energy and
it's
correct
just
or
like
Those
you need to
bonds.
start the reaction, right?
The energy needed to start a reaction. Why do we need energy to start a
You
reaction?
gotta break and make bonds.
It's like that egg.
Okay, so
you
sometimes
can't
we think about it in terms of making and breaking bonds, but
Sure you can.
another way of thinking about it
You gotta just drink the egg.
is to actually think more about this collision. So I want to start with actually this, what's called an SN2 reaction. I'm doing a little bit of organic chemistry for you guys.
no thanks.
So this is a very common type of reaction in organic chemistry. And so they're going to show us the mechanism.
Oh, wait,
All right. So in this type of reaction, we have some hydrocarbon here. There's carbon. These are going to be either other carbons or hydrogens. We've got some X, that's a halogen. And what happens in this mechanism is that some other substance, some other particle comes in and collides with that carbon and eventually pushes this thing away. All right? So it's a bimolecular reaction. But here's a better example, right? So we have bromomethane. We have an OH coming in here. The OH collides with the bromomethane and eventually sends that bromine off. But what they're showing us here is that for a brief period of time, for a brief period of time, once those particles collide, we're going to be in the process of forming this eventual bond here, but we haven't exactly broken this bond here. So we have this thing that's created, just very, very briefly, that's sort of on the way to becoming our product, right? It's on the way there. We call it a transition state. It's part of the transition from our reactants to products. Okay? So this would be a great picture of a transition state. It's basically, if we think about the CH3Br and the OH being here, the CH3OH and the Br being here, this peak right here represents this point where we're trying to get all those things to come together. This molecule that they've shown up here. That's what we call a transition state. And in this diagram here, we've got 3 steps. That means we have 3 transition states. Running out of colors here. So we've got transition state 1, transition state 2, transition state 3. Now, we talked about rate laws, and if we experimentally determine the rate law, and it's first order in H2 and it's first order in O2, that means in one step of our mechanism, one molecule of H2 and one molecule of O2 are colliding, right? If we experimentally find that the rate law is second order in H2 and first order in O2, then maybe all 3 of those particles are colliding at once. But what happens if we find that the true rate law for this reaction is just first order in H2? Or just first order in O2? What does that mean? means that the concentration of hydrogen has no effect on how fast the reaction occurs. How is that possible?
It's not part.
It's not part of the slowest step. Okay, what is part of the slowest step? O2. And it looks like only one O2. So that means that in our mechanism, some step, maybe it's step 1, maybe it's step 2, I'm just going to say it's step 1. But that means O2 is the only reactant in the slowest step. We call that a unimolecular elementary step.
You know what?
Unimolecular. One molecule. What can one molecule do?
Separate.
It could split. Maybe this splits into two O's.
You could also read it.
Can it really do that all by itself? Is an O2 just going to be chilling out and then all of a sudden, I'm just going to split into two?
Energy.
No. But it's possible that there are other molecules around this thing that are colliding with it, right? And when molecules collide, they start shaking and vibrating, right? And maybe something hit it with just enough energy that it actually broke that bond. Whereas the thing that hit it didn't break itself. Okay, so it could be some background molecule, maybe some solvent. Maybe you're doing this and there's nitrogen also in your container, right? So maybe there's a nitrogen molecule flying around and it's at the top end of our Maxwell-Boltzmann distribution, and so maybe it's got a lot of kinetic energy and it just smacks right into this O2, splits it apart, but the N2 is left unchanged. Well, then the only thing that underwent a change is O2, so that could be a unimolecular reaction, okay? It's not truly a collision of one particle, that's not possible, right? But only the one particle actually underwent a change. It was colliding with some background molecule in order to undergo this change.
So could something like O2 undergo radiation?
Undergo what?
Radiation.
What do you mean radiation?
Alpha, beta, gamma, like any of that?
That depends on the composition of its nucleus. We haven't really talked about nuclear chemistry. That depends on the ratio of protons to
Well,
neutrons.
couldn't that, well, no, I'm saying, couldn't that also be a unimolecular thing?
Sure, alpha decay you could consider to be a unimolecular reaction, right? So it's one unstable nucleus that then breaks apart into an alpha particle and some other. Yeah, this reaction could also occur because of ultraviolet light or X-rays or something, are shined onto this molecule and excite the electrons, those bonding electrons, to the point where the bond breaks. Okay? But most of the time we think about it as some sort of background collision. Okay? But so it's possible that this is the first step, then maybe the O combines with an H2 and forms H2O, then the other O combines with the other H2 and forms the other H2O. Okay? So maybe this is the actual mechanism. And I think it makes sense from a bunch of reasons that O2 just splitting apart is probably going to be the slow step. Right? Once this splits apart, it'll probably be pretty easy for the O to then go in there and grab onto some H's and form your H2O, okay, whatever. But yes, if this is the slow step, then the rate law for the slow step is K times O2 to the first, which would match our experimental rate law. Okay? All right. Talked about intermediates. That's 4C3. 4C2, the rate is set by the slowest elementary reaction or rate limiting step. Talked about that. 4C2. 4C1, the mechanism of a multi-step reaction consists of a series of elementary reactions that add up to the overall reaction. Talked about that. Boom, we just did 4C. Well, we did the background, we haven't done any practice on it. We will do lots of practice on it. And actually, if you look at 4B3, we did 4B3 in talking about this energy profile. 4B1 was just the definition of an elementary reaction. Gentlemen, 4B1 is the definition of an elementary reaction. You have to understand that these steps in the mechanism are actually describing collisions. Elementary reactions actually describe collisions. And only because they actually describe collisions can we write a rate law just based on the coefficients of that elementary reaction. All right, 4B2 is about the Arrhenius equation and how not all collisions are successful and why. So we covered that yesterday. So next week we'll basically have to do a whole bunch of practice problems and show you kind of what types of questions to expect. We'll talk a little bit more about catalysts.
Do I stop it?
Please.